way after lunch. Okay, don't put metal in it. Here is a, yeah, it's old. I'll check it out. I'll call the microwave company and see what they can do. But thank you for noticing it and stopping it. It's important to remember that at any point of tangency, watch this. If you have a function, let me redraw it. Let's say that this is, ooh, that's not quite a function. Let's say this is a function, f of x. At any point of tangency, let's draw this one right there. At any point of tangency, and by point, we'll call it at x equals c. Okay, so at any horizontal location, the function f of x and the tangent line we'll call t of x, they share two things at that x value. Do you know what they share? They share a y value, right? They share a y value. So f of c is going to equal t of c. We know that. And what else do they share? They share a slope value. Yeah, you can scroll down and read that. So they also share a slope value. So f prime of c is going to also equal t prime of c. Later on in the year, when we get into Taylor polynomials, you'll see that this is true for all polynomials, not just linear polynomials that we use to approximate other curves. They have the exact same value at the center of the approximation. That's what we call it. So x equals c is a good letter to use for that, because we can say that's the center. Now, just kind of thinking of why we would want to do that, notice that for values that are near c, like within a certain radius, go a little bit to the left and right, the tangent line becomes a decent way to approximate the function value. The further away you get from c, you know, the more they start to diverge from each other. But they have the exact same value at c, and in the neighborhood of c, they're close to each other. But that's later. Right now, we just remember at any value of x, a function and its tangent line share two things. What are they? A y value and a slope value. Good. So they have the same f value and same f prime value. Here's a nice application. Find the value or values. Ooh, look at that. We call that mathematical foreshadowing, right? Ooh, could be more than one. Of k, such that the line 5x plus y equals -9 is tangent to the graph of 2x squared plus kx minus 1. All right, so first thing we need to notice is k is the linear coefficient in this quadratic function f of x, which if you remember from completing the square days, it's kind of responsible for the horizontal shift on this opening up parabola. So this line does not have a k in it. We know where this line is. This line, if we put it in slope-intercept form, we can identify some parts, yeah? Let's go ahead and solve this for y. I would get y equals -5x minus 9. So here's your tangent line. We know it has a y-intercept of -9, and it's down 5, right 1, or up 5, left 1, right? That's its slope. So that can't move throughout the coordinate plane. But this function can. I need to find the k value, just kind of see what we're doing here. I want to find the value of k so that when I have a parabola that opens up, and again, I know it opens up because of the 2, I want this line over here that has a -5 slope, right? I want this line to be tangent to this graph. So something like that, right? I need to find that value of k so that it's tangent. All right, so how do we even proceed with something like this? Guess and check? No. We need to realize that this is the problem where we need to take advantage of the fact that at the point of tangency, bless you, at the point of tangency, the function f and the tangent line y share two things, right? They share a slope value and a y value. Let's go ahead and proceed to see if that gets us anywhere, right? We have to equate two things. So let's go ahead and equate the y values. And I'm just going to go ahead and y values. If you put a colon, y values colon, that means, hey, I'm going to be over here working on the y values, right? Now, if we hadn't done so, now would be a good time to solve the tangent line equation for y, -5x minus 9. I'm going to set that equal to the function, right? Which remember, f of x is just a fancy word for y. So 2x squared plus kx minus 1. 2x squared plus kx minus 1. Sweet, right? Now, if you look at that equation right there, the problem with it is it doesn't have a unique solution because it's one equation with two unknowns, right? We have an x and a k. And if you remember from Algebra 2, if we're going to have a unique solution, which is what we want, right? We're unique unicorns. You have to have as many pieces of information or as many equations as you do unknowns. So with two unknowns, k and x, 1, 2, I need how many equations? 2. But I only have 1. I need at least 2. You can have more than 2. Well, where in the heck am I going to get myself another equation? I mean, I've already set the y values equal to each other. The slopes must be equal to each other as well. Let's go ahead and find their derivatives then. If this is y, then dy dx, or y prime. What's the slope? What's the derivative of negative 5x minus 9? Negative 5. Yeah, you could do that by the power rule, or you could just say, oh, it's a line, the slope is constant. Okay? And over here, f prime of x, I'm going to do it off to the side here from my graph. Oh, boy. Here, let me move this over. The derivative of 2x squared, that's 4x to the first. What's the derivative of kx? K, right? It's a constant. And then the derivative of minus 1? 0, right? Absolutely nothing. So now I can set those equal to each other. So slopes, colon. I'm going to go ahead and do the f prime first. 4x plus k has to equal negative 5. All right? Now, what I've done is I've created myself a system of equations, right? And so we can solve those either by substitution, elimination, Kramer's rule, right? Augmented matrices, matrix, yeah. But really, substitution is probably going to be the way to go, right? So if you want to use substitution, you can solve either equation for either variable and plug it back into the other. Look at this slope equation. That one's pretty easy to solve for which variable? K. All right, just solve for K. So over here, we get K equals negative 4x minus 5. Go ahead and put a box around that. Does that answer the question? It said find the value or values of K. Is that a value? No, it's not. But I'm going to box it because I may have to come back to it. For now, what I'm going to do is I'm going to plug it back in way over yonder. And you don't have to draw arrows. Yeah, you could draw arrows for yourself, but on the work, you don't have to. And now, when we're shifting gears, when we're going from one idea to another, it's a good time to say, so, right? We get negative 5x minus 9 equaling 2x squared plus k, which is negative 4x minus 5, x minus 1. So to highlight what I'm doing here, there's k and there's k. I don't like my 4 there. That 4 is kind of, yeah, it's janky. Janky. Oh yeah, I don't want janky k. K is my letter, you know. I gotta make it look non-janky. It's too much of a curl going, you know, like my hair here. All right, so now all we have to do, since we have one equation with one unknown, expand it out and see what happens, right? I think I'm going to have an x and an x squared and maybe a constant, but we could do that. We could solve quadratics. So let's see, the left side, negative 5x minus 9 equals 2x squared. I got to distribute the x from the right-hand side. Okay, minus 4x squared minus 5x. It's not every day you get to do that, right? Now, I don't like negative leading coefficients. Keep your hand down if you don't either. That's what I thought. Oh, you do like negative coefficients. Oh, okay. Yeah, I said keep your hand down if you don't like them. Yeah. I'm going to bring everything over to the left. Bring everything over to the left. So I'm going to get positive 4x squared, positive 5x, negative 5x is already over there, negative 9 is already over there, plus 1. So however you want to take inventory. What's that? Oh, yeah. And 2x squared be negative 2x squared? I'll just put them in the front. I don't like negative. Oh, can I combine them first? Is that what you're saying? Yeah. Yeah, that makes more sense. There's more than one way to eat an apple, right? As they say. I don't know if anyone says that. Yeah, negative 5x minus 9. Combine like terms. That's negative 2x squared minus 5x minus 1. Okay. I still don't like negative exponents. Hey, look what happens to the negative 5x's. They cancel from both sides. So if you didn't even want to write them, you wouldn't have to do that. So now I'm just going to bring this becomes positive 2x squared. And then I'm left with a negative 9 plus 1, which is a minus 8, equals 0. So however you want to do it, the algebra, right? You got to be real careful with the algebra. And now the first rule of factoring is to factor out any common factors. So I pull out the 2 and I get x squared minus 4, which, hey, that's the difference of 2 squares, which factors into the product of 2 whatchagets. Do you remember? Conjugates. Y'all do remember. That's like the best clue that I've ever given. Whatchagets. Yeah, no one ever says, you know, antijugates. They always say conjugates. I don't know what else you would say, right? So, and you don't have to say so, but you could just x equals negative 2 or positive 2, or you can list it as conjugate pairs. Now, you got to be careful here because I could box those up, right? Box those up. There's my answer. I walked away. I did some math. There was even a little bit of calculus involved, right? Or if this is a free response question, it might say, which of the following is the value of k? And answer choice A is 2. Or answer choice A is negative 2. And you're like, confirmation that I got the right answer. But is that what we're looking for? No. The last step to any problem in here is to answer the frickin' question. And I don't care if you say frickin' or friggin' with a G or a K. Okay? A friggin'. Answer the friggin' question. What values of K? Oh, I just found X values, didn't I? Oh, right. So now I got to go back over here. So, okay, let's just do this. When X equals negative 2, comma, K equals, and I plug it in and I get 8 minus 5 is 3. And when X equals positive 2, comma, K equals negative 9. Oh, so the mathematical foreshadowing alluded to the possibility of being more than one. Speaking of alluded, that's not Miss Calder's name either, right? It's not Elena. It's not alluded. It's Allura. Yeah, I apologize to her at lunch, but she's cool with it. She's cool with it. Thank goodness. But I'll call her Allie now. And there it is. So if this were a free response question, notice how I answered it. I kind of didn't just say K equals. I kind of showed what I was doing. Yeah. It's not negative what? Negative 8. Yeah, it's not negative 9. What was I doing? It always happens at the end, doesn't it? Negative 13, right. It always happens at the end. That's where I make my careless mistake. Always. It's the last thing, and then my brain is disengaged. But thank you. Yeah. All right. Now, one of those, if this were a multiple choice question, maybe one of those would be an answer choice. So answer the friggin' question, and then I'm going to add to this. Run through the tape at the end of the race. I didn't do that, right? I did not. I got to the end, and I'm like, no, I'm good. I'm good. I'm just going to put the wrong answer and walk away. After all that hard work, you got the wrong answer. Oh, careless mistakes. Okay. Now, what that means is there's two parabolas, right? There's a parabola that's 2x squared minus 2x minus 1, and there's another, plus 3x minus 1, and another parabola that's 2x squared minus 13x minus. I wonder what that looks like to have two parabolas that are tangent to the exact same line. Well, you're in luck. There they are. Look. Here's the solution curves to the problems above. So the one on the left is the negative 13. The line is the same in both of them. It's not an optical illusion. But notice the one on the left, it's tangent at positive 2. And over here, the one on the right with the K is positive 3. It's tangent right there at negative 2. So There's two parabolas. All right, we found the value of k. There was a lot of algebra in there, wasn't it? Yeah. Good old algebra. Love that algebra. The algebra is the mechanics that makes the calculus engine work, you know. But you can bog down in the engine quite a bit. In fact, that's where usually the engine problems occurs, in the engine, right? No kidding, right? True that. All right, any questions on that? That's a good application. Y values are the same, slopes are the same. When in doubt, if you don't really know where the road's going to lead you, start with something that you know to be true. I had two things I could equate, and boom, I was led to the right answer, okay? Algebra led me there. All right, now shifting gears here, we're going to memorize all the trig functions derivatives eventually, and all of the inverse trig functions eventually. This class has a lot of memorization, and last year, that's why the AP results were the worst ever under my tenure here, is because no one had to memorize anything for my tests, although I encouraged them to, right? So when it came time for the AP exam, they hadn't memorized anything, and of course, if you don't know it, you can't use it, right? You can't access it, because we had everything equal last year. It was all take-home tests because of the online learners. And so even though I said, hey, memorize it, they're like, yeah, right, sucker, right? Or something like that. Memorize as you go. It's a lot easier than trying to cram, because you do want to memorize things. Certain things you have to memorize, and then they become part of your mental catalog, and you know they exist. You can't really even think about accessing something unless you know it's there, okay? So this box contains two derivatives. I call this the sine and cosine rule, for lack of a better name, because in here we have the derivatives of sine and cosine. And there's the first one. Notice the verb is in front. The derivative with respect to of sine of x is cosine of x. Yeah. And what's the derivative of cosine of x? It's not sine, it's negative sine. Now, here's something that'll help you as you remember everything going forward. Anytime you have a derivative of a circular trig function, any one of the six we know, if it has a co in the name, whether it's cosine, cosecant, cotangent, or later arc cosecant, inverse cotangent, if it has a co in the name, its derivative is going to be negative, okay? And if it doesn't have a co in the name, its derivative will not be negative, okay? That'll help you. So what's the derivative of sine? It's just cosine. But what's the derivative of cosine? Negative sine. Yeah. Now, you could verify this. I think we did this in 1.4 on the worksheet. You know, you could say the limit as h goes to 0 of sine, oops, I put an S. I don't want to abbreviate that. Sine of x plus h minus sine of x all over h, right? And to expand this, you had to use the composite identity for sine. Or we did one in class, and you didn't know what it was for, and we did one in the worksheet. But if you expanded this using the composite identities, and then you grouped two of the three terms together by putting it over the denominator, you will eventually end up with cosine of x. Okay, we don't want to have to reinvent the wheel every time we need it. So the derivative of sine is cosine. All right. Now once we know that, look at a little stuff we could do. Find the derivatives of each of the following. Y equals 2 sine of x plus 7. Let's find its derivative. The left side becomes dy dx. And what's the derivative of 2 sine of x? 2 cosine of x. Good. The 2 just goes along for the ride, remember? Remember here? Constant multiples are there in the beginning, they're there in the end. I'm sorry about that tragic story I told you. The derivative of 2 sine of x is 2 cosine of x. Okay, and what's the derivative of the next term, plus 7? 0, so we don't have to write it. You don't really need parentheses around a trig function. Okay, I put the x there to show the separation from the plus 7. But by default, if you ever have like sine of ax plus b, okay, we read this as sine of ax plus b. That's the default for any trig function. or natural log as well, okay? If you have multiple terms following a function, if you intend it to be part of the angle, then you have the obligation, the onus is on you to put parentheses around it. Otherwise, everyone's going to read it as the first term only that follows the trig function or natural log is the argument, is the angle, okay? Does that make sense? So if I had just written 2 sine of x plus 7 without parentheses, you wouldn't say, is the angle x or is the angle x plus 7? You would realize that it's still the same, okay? So the derivative would still be 2 cosine of x. That's a good thing to kind of point out in the beginning. All right. What about this letter B? I have 2 terms. Are they both in ready to go power rule format? Well, the first one is in power rule format, but the second one, how you take the derivative of cosine? Is it x, you multiply 1, so you get cosine of x to the negative first? Is that 1? Is that how you use the power rule on a trig function? I don't think so. Yeah, it's just negative sine. So here we go. This equals derivative of x is 1, and the derivative of cosine is negative sine of x. How am I doing? Is that good work? That's not good work, because what did I not do on the left side? I didn't do f prime of x. You're going to get, you did it. You did it. Don't forget the equal sign, though. You're going to get excited. You're going to get excited. But make sure that if it's in noun format, you have an equation, you need to do it to both sides. Okay? Now, let's do something here. Let's go ahead and jump to example. We have time. Example 11. We have till 35? Yes. Okay. If f is sine of x, find the following. The slope of the graph at 0. All right. Let's go ahead and review how to sketch y equals sine of x. Sahala. All right. Y equals sine of x, also known as axis high, axis low, axis. Sahala. Sine is axis, high axis, low axis. The period is 2 pi. Yes? That's the length of one cycle. So if you come out here and call that 2 pi, half of that is pi, half of that's pi halves. That's your quarter cycle counting interval now. So whatever your width is on your paper, you got to try and keep that same width going. So 1 pi halves, that would be 2 pi halves. The next would be 3 pi halves. 4 pi halves is 2 pi, so on and so forth. And then if you needed to like add more, you just try and eyeball. You keep that same quarter cycle distance, and then you can label them, right? 0 is one of them. And then you get negative 1 pi halves, negative 2 pi halves is negative pi, negative 3 pi halves, negative 4 pi halves is negative 2, so on and so forth, right? There's no shift here. And then it goes up to 1, and it goes down to negative 1. That's the amplitude, stays between the range of negative 1 and 1. So for sine, it's Sahala. So I'm going to choose, I'll choose this nice light blue here. So axis high, axis low, axis. That's how we know to sketch sine. And then you just keep following the pattern in reverse or forward, you know, if you need more points, whatever. And I always connect them in like quarter cycle intervals, so they don't look as smooth as some of y'all's. Now, let's quickly look and see why the derivative is cosine, yeah? Because we'll do this on the calculator when we come back to 2.2, but we could do it without the calculator. If I sketch, and let's go ahead and label this as f equals sine of x. If I were to sketch the derivative at the same values of x, then what I'm really plotting at the values of x, where I have y values, is I'm plotting their slope values. So where on this graph do we know for sure 100% the value of the slope? At pi halves, 3 pi halves, negative pi halves, and negative 3 pi halves, because the tangent line there is what? 0. Well, the tangent line is horizontal, and therefore the slope is 0, and therefore the derivative is 0. So at pi halves, I'm going to use a different flavor here. I'm going to plot the slope. So anywhere you have a local max or a local min, go ahead and put an x-intercept. And now all you got to do is look at it in between there. Let's look from negative pi halves to pi halves. Notice on that interval, the graph of sine is increasing, yes? And because the graph is increasing there, we know that its slopes are going to be positive. Similarly, between pi halves and 3 pi halves, that's where the graph of sine is decreasing. We know that then the derivative graph will be negative. So on and so forth, right? And you can continue doing this. So I'm just shading regions. I'm going to sketch the graph in that region. Now let's look at the origin of sine. I'm going to use my, it might be better if I do it on here. Let's go ahead and get out a curve surfer. What's a curve surfer? A curve surfer is basically a tangent line. There's my curve surfer. And what's cool with, Notability is you can animate it. So look right there. I'm going to go from pi halves. I lost it. I'm going to go from pi. I need to give it a big enough handle. Okay. I'm going to go from pi halves up to pi. Look at what the slopes are doing. Okay. It's 0 there. As I go to the right, I'm surfing the curve. So my tangent line is getting steeper. And look at the origin right there. That's kind of where the graph is the steepest in the positive direction, yes? Because then after that, look what happens to the slope. They're still positive, but now they're decreasing, approaching what again? 0. So they're positive the whole time, the slopes are. But they go from 0 to like some maximum slope back down to 0. So that's kind of cool. So guess what that maximum slope is? 1. And when I go down in the other direction, oops, when I come down, here, bigger handle. When I come down here, notice that's where it's the most negative at pi, and then it starts increasing again towards 0. Guess what the most negative value of the slope is? -1. So boom, boom, and then yeah. So basically, we call that an inflection value. That's where the curvature is going to end up changing. We're going to say that the graph goes from concave up to concave down. So now we can actually connect it, and it's actually 0 there. We got that point. I'm using a different flavor now all of a sudden instead of the pink. Bless you. But there you go. There's the graph of the derivative. I guess I should keep it the same color. And of course, we recognize that as Cha law, right? Cha law is cosine high axis, low axis, high. So when I start at 0, I'm at a high point. Now, how do I know that the high point goes, the maximum slope is 1 and -1? We're actually going to figure that out next time, okay? It says to find the slope of the graph of f at 0. Do we have time? We have like 20 seconds, okay? So there you can visually see how you can generate the graph, okay, of a derivative of something by hand. And sometimes you recognize it, sometimes you don't. We're going to pick up with example 11 tomorrow, and we should be able to finish the notes tomorrow real easily, okay? So t-shirt ideas, I think, are in the work. Be working on the worksheet for 2.3, okay? Have a fantastic, awesome, super wonderful rest of the day.